Welcome to the Are You GCSE Physics Ready playlist. This playlist is packed with example questions and guided solutions for every GCSE Physics topic. So it's the perfect tool to help you test your understanding. If you feel like you might need a quick review of this topic before having a go at the questions, or you would just like the ideal revision companion for these videos, then do make sure to download my free GCSE Physics revision notes, linked in the description below. If you're ready, let's dive in. Okay, question number 1 is using Sankey diagrams, and it is to draw a Sankey diagram of this bulb, which is transferring 95 joules to the room and 5 joules of light or thermal heat itself. So, first thing to do with your Sankey diagrams is to pick a scale. So I'm going to choose that 1 centimetre is equal to 5 joules. Then I need to work out, okay, what are the widths of my different arrows going to be? So the first one, which is the width for the light/thermal energy, that 5 joules there, what you can do is you can take your 1 centimetre multiplied by 5, as in the 5 joules of energy, divided by 5 my scale, because remember each 1 centimetre is worth 5 joules. And since there is only one 5 joules here, that should be 1 centimetres long. To work it out for my 95 joule thermal energy, I do the same thing. So if 1 centimetre, 4, and then this time I need to work out how many 5 joules there are in 95 joules. So 95 divided by 5 is 24, so that should be 24 centimetres. And then for my total input into my bulb, that is the 95 joules plus the 5 joules is 100. And doing the same thing again, there are 25 5 joule segments in 100. So that line should be 25 centimetres long. So I will have a Sankey diagram that looks something like this, although my Sankey diagram has not been drawn to scale and is not particularly good because that small arrow would be a lot thinner, but just so that you can see where I've got my input 100 joules going into thermal or light 5 joules and thermal or room 95 joules. Okay, now I'm asked how efficient is the bulb, so I'm just going to bring those numbers over from the slide before. We had 95 joules wasted to the room, 5 joules useful light the bulb, and 100 joules that was being inputted into the bulb. So as always, first things first, we just need our equation. Efficiency is my useful energy divided by the total energy. So that is 5 divided by 100. Remember, my input energy and my total energy are the same thing. So that gives me 0.05. And it's fine to leave your efficiency like that, and your efficiency has no units. However, if I did want to change that into a percentage, then all you do is multiply that final number by 100. So for me here, that's 0.05 times 100 is 5% efficient. Okay, let's have a look at the first question on the left, which is what is the efficiency of a kettle which has an input of 7 kilojoules and output 4.5 kilojoules of thermal energy to water. So first, let's just start with our equation. Efficiency is useful over total, and then to find my total energy, which again is the same as my input, and that is 7,000 joules because it was quoted to me in kilojoules. Now, as it stands for this question, because both of my energies are in kilojoules, I actually could have just left that number as 7. But if you ever have something where your question is mixed between joules and kilojoules, then you would have to convert the kilojoules first. So I'm going to leave this as converted, and I'm also going to convert my useful energy there, that 4.5 kilojoules, into 4,500 joules. Okay, so my efficiency is just that useful over total. 4,500 divided by 7,000 gives me the 0.64. Next question, what would be the amount of energy wasted if the same kettle were only 22% efficient? So same kettle meaning it's been given the same amount of energy from the supply. So 22% efficient, if I divide that number by 100, that gives me 0.22 for my efficiency. So what I've done there, if you remember, to get my efficiency into a percentage, I multiplied by 100. So to go from the percentage into the efficiency, I've divided by 100. And so I can write this. My useful over my total should equal 0.22. So I'm going to plug my 7,000 in there, useful over the total, which was my 7,000 joules from the previous question, is 0.22. So to find useful, I need to multiply both sides of that equation by 7,000. So I get useful equals 0.22 times 7,000 is 1,540. But it did not ask me the amount of useful energy, it asked me the amount of wasted energy. So now I need to think about what that means. Well, your wasted energy should be equal to your total energy minus the useful energy, and that's 7,000 minus 1,540 gives me 5,460 joules. Okay, and following on from that question, we have how much energy would have to be input to get the same original output of useful energy. So remember, originally my useful energy, and I've just taken this from the previous question, was 4,500 joules. And now my kettle has this efficiency of 22%. Okay, so I have to work out how much energy in total I'm going to have to put in to get 4,500 joules out of this kettle, which is 22% efficient. So I look at my efficiency equation again. Efficiency is useful over total, and I'm going to fill in the gap. So 0.22, remember I've changed that percentage by dividing by 100 into my efficiency, equals 4,500, that is my useful, divided by my total. So this time, to get my total, I need to take that 4,500 and divide through by 0.22. 20,455 joules. Okay, now time to work out which device here is more efficient. So I've been given two devices, and the first one is an LED which transfers 20 joules to light and 75 joules to heat. Okay, so let's work out how efficient this LED is. So efficiency is useful over total, and my useful here is going to be that 20 joules, okay, which is associated with the light bulb itself. And that 75 joules is not going to be the total energy. That's actually my wasted energy, energy which is used to heat the surroundings. So in order to find what my total energy is here, I need to add those two together. My useful plus my wasted is 95 joules. Good, now I can do my efficiency. It's useful 20 over total 95 is 0.21. And if I wanted to convert it into a percentage, I times it by 100 and get 21%. Okay, now the second device has 82% of inputted energy is wasted. Okay, so that's the amount of energy which is wasted. So if I take 100 and minus that 82%, that will tell me the percentage of energy which is used for useful things. So that is 18%. So now I've got two percentages, I can just compare them like for like and see that the LED is more efficient because it has this higher percentage efficiency. Okay, now time for some more wordy questions. So we have explain why the lid on a kettle helps to make it more efficient. Okay, so you need to be mentioning what it is about the lid that is contributing to that efficiency. So the first thing and kind of buzzword is it is providing insulation. Okay, that lid is providing a cover and then for insulation for your kettle. Then you need to go on to explain why insulation helps the efficiency of this kettle. So you can talk about the fact that insulating something means that less heat will be dissipated to the surroundings, and it's a really good idea to write the word dissipated in your answers about efficiency, which therefore means that more of the inputted energy into your kettle can be transferred to useful forms. Okay, so that's me showing that I know exactly what the definition of efficiency is. It's useful over total, and it could be use. I would advise actually even writing your equation down in an answer to this in the exam. Okay, so you can say you're maximizing that amount of useful energy that can be transferred. Okay, and the second question, explain why adding oil to a motor can improve the efficiency of the device. So now, what is the oil providing? And you might want to talk about the fact that the oil is a lubricant. And the importance of that, of course, is to help reduce the friction of your motor. So you always want to establish that it's all about reducing the friction here because you're using this lubricant. And then you want to go on to explain why reducing the friction would affect the efficiency. So because there would be less work done by the friction, because the friction is smaller, then you can have less energy transferred into heat energy. Because remember, friction doing work is the thing that transfers useful energy into heat. So again, more of the input is transferred into useful forms. Okay, and energy transfers. So number one, what are the energy transfers between a ball thrown into the air? Okay, so when you throw a ball into the air, initially it has lots of kinetic energy because it's going really fast, and then it gets slower and slower and slower as it goes up and up and up in the air. But as it's traveling up and up and up and up in the air, it's getting higher and higher and higher, so it is gaining gravitational potential energy. So you have the idea, you've got kinetic energy going to gravitational potential energy. And what is happening is your ball is actually doing work against gravity, and that is what is transferring that energy. So it is a force. It is your gravitational force transferring that energy. So you can say that that transfer has been done mechanically. Mechanically can often be the one which is hardest to decipher for your energy transfers, but you could have done it by process of elimination, which would be a top tip. It's not going to be heating, there aren't really any temperature differences involved, there aren't any charges involved, it's not electrically, there aren't really any waves involved either, so it's not radiation. Okay, next one. What is the energy transfers of an electrical heater? Okay, well, from your mains, it depends how far back in the chain you go, but maybe it's mains, maybe it's battery operated. Either way, at some point there will be some chemical energy which is being transferred into thermal energy of your heater. Okay, and because it's an electrical one, that is happening electrically. Some charges are doing some work to make that energy transfer happen. Okay, and what is the energy transfer of a wood fire? So again, we've got the same final result here. We've got something that would heat our room, but this time chemical energy stored in the wood, in the fuel, to thermal energy, but by heating. Okay, and that's the temperature difference then that you get between the wood and then the heat that you get once you burn that wood. Just before we go into the tips and tricks section, if you do want some extra advice to getting that grade 9 for your GCSE, then why not download my free 20-minute exam success guide? Just click on the link in the description below. I'm going to give away all of my best advice and secrets, and completely for free, so why not? Okay, so my first tip or trick is to avoid using sound or light when talking about energy stores. I know I've done it for light and have been a bit lax in my examples, but that was more to make it obvious which my useful form of energy was for a light bulb. In your GCSE, you should avoid using it and you should talk about thermal energy instead. I've written electrical here because, again, another thing that students often get wrong is electrical isn't a type of energy store. You can't store energy. Electrical in an electrical energy store, but you can transfer energy electrically. Okay, so make sure not to get those two mixed up. Work done in friction, if there is something like a mechanical process, so maybe it's a car slowing down on a road, and there is energy which is being wasted as heat or dissipated, you should always talk about in your explanation work done by friction, which is transferring that energy into heat. Efficiency percentages, remember you can take your efficiency, if you multiply it by 100, that will give you your efficiency as a percentage. Oh yeah, efficiency and power. So in your equation, you have useful energy over total energy for your efficiency, but it doesn't have to be energy. You can use powers as well. And finally, a closed system, just remember that you do need to know the definition of it, that there is no net energy change in a closed system. Okay, so because of the conservation law of energy, energy is not created or destroyed. The universe is a closed system, but there might be individual systems where you haven't considered enough objects that are not closed systems, so that the total energy in doesn't equal the total energy out, okay, because you're not considering, let's say, the surroundings as part of that system as well.